My name is Ricardo Garcia, and today I will be showing the applications of Calculus 1 in electrical engineering. So, what exactly is electrical engineering? At its core, electrical engineering is the study, design, and application of electricity, electronics, and electromagnetism. These are the forces and principles that power almost every part of our modern life, from the devices we carry in our pockets to the cars we drive, and even the medical equipment that helps save lives. Electrical engineering has many branches. Some of the main ones include power systems, which focuses on generating, transmitting, and distributing electricity; electronics, which deals with circuits and devices that use electricity to process information; control systems, which make sure machines and processes behave as intended; and signal processing, which is used in everything from smartphones to medical imaging. Each of these areas focuses on a different aspect of electricity and electronics, but they all share a common goal: to understand and control electrical energy to improve our lives. Personally, I am drawn to this field because it offers job stability, which is increasingly important in today's uncertain world. But beyond stability, I am passionate about renewable energy. Electrical engineers play a huge role in designing, improving, and implementing sustainable energy solutions like solar panels, wind turbines, and smart grids. Knowing that your work can both innovate and make a tangible difference in the world is incredibly motivating. Now let's move on to something more technical: the derivative of a voltage time graph. In simple terms, a derivative shows how fast something is changing at a particular moment. In my case, this tells us how quickly voltage is changing over time. But why does this matter? Sensors. Sensors measure things like acceleration, temperature, or pressure, often produce voltage signals. By analyzing the derivative of these signals, engineers can detect subtle changes much more accurately than by just looking at the raw voltage. For example, imagine a voltage graph from an accelerometer in a car. By looking at the derivative, we can see exactly when the car is accelerating or decelerating rapidly. This information is critical for safety features, medical monitoring, or even modern technology like smartphones. In essence, derivatives help engineers turn raw data into actionable information. They allow us to predict, respond, and automate systems in ways that make life safer and more efficient. One real-world application of voltage derivatives is in airbag deployment systems in vehicles. Inside of a car, accelerometers constantly measure motion. When the car experiences a sudden impact or change, the voltage in the sensor spikes rapidly. By analyzing the derivative of this voltage, the system can determine whether the car is in a crash and if the airbags should or should not deploy. Without this technology, airbags might deploy unnecessarily hard or unnecessarily during hard braking or fast acceleration, which could actually be dangerous and costly. Using derivatives allows the system to distinguish between normal driving and an emergency situation, ensuring that airbags deploy only when truly needed. This is a perfect example of how a mathematical concept, which is derivatives, directly saves lives in real-world scenarios. And it's not just theoretical. This is applied engineering that happens in every modern vehicle on the road today. Heart rate monitoring. Derivatives are also crucial in heart rate monitoring, which is especially important in medical and fitness technology. Devices like PPG heart rate monitors use light sensors to detect blood flow and measure your pulse. But other signals, such as bright hospital lights or even sunlight, can interfere with readings, causing inaccurate measurements. By applying first and second derivatives to the sensor's voltage signals, these devices can filter out noise and pinpoint your heart rate more accurately. This technology is used not only in fitness trackers, but also in hospitals, where precise monitoring can make a crucial difference in patient care. In other words, the same principle that helps airbags deploy safely also ensures that your heart rate is monitored accurately. This shows the versatility of electrical engineering. One concept can solve problems across multiple fields, from automotive safety to healthcare. Phone light sensors. Another everyday example is phone light sensors. Have you noticed that your phone sometimes turns on the screen when you get a notification and sometimes it doesn't? This is not random. It is controlled by light sensors that detect your environment. These sensors use voltage measurements, and by analyzing the derivative of these readings, your phone can determine whether the screen should be on or off when you receive a notification. If your phone is in your pocket or face down on a table, the screen stays off, which helps preserve battery life. Even small devices, like phones, benefit from the same engineering principles as airbags or medical monitors. This shows that electrical engineering is everywhere, even in devices we take for granted every day. It is a field that combines technical knowledge with practical problem solving in ways that touch nearly every aspect of modern life. To wrap up, let's review the key points. Electrical engineering is the study of electricity, electronics, and electromagnetism. Voltage derivatives are a very powerful tool in analyzing how sensors respond to changes. These concepts are applied in real-world technologies such as airbags in vehicles, which save lives, heart rate monitors, which can also save lives or improve healthcare, and phone light sensors, which makes devices smarter and more efficient. And finally, electrical engineering offers career stability and opportunities to work on innovative solutions, including renewable energy and sustainable technologies. In short, electrical engineering combines creativity, problem solving, and practical impact. It has a very broad field of applications and can be used in many day-to-day activities that aren't often thought about.